This video is brought to you by mywayteaching.com.
So, because of the drift, there will be a net transport of charges across any area perpendicular to electric field E. Okay. For example, consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Okay, as you can see in this particular figure. So, because of the drift in an infinitely small amount of time, that is delta t, all electrons to the left of the area at distances up to Vd delta t would have crossed the area. See, if n is the number of free electrons per unit volume in the metal, then there are n delta t Vd into A. Number of electrons are there. Since each electron carries a charge minus E, then total charge transported across this area A to the right is given by minus Ne A Vd delta t. Okay. E is directed towards the left and hence total charge transported along E across the area is negative of this. So, the amount of charge crossing the area A in time delta t by its definition is I delta t, where I is the magnitude of current. So, we can write I into delta t is equal to plus NEA Vd into t. So now we can substitute the value of Vd that we already know, which gives E square A by m tau delta t E. So we know how I is related to density, isn't it? So from these two equations we can write J is equal to N E square by m tau E. The vector J is parallel to E. So J is equal to N E square m tau into E. See, in comparison, if we observe this equation, it is exactly equal to the Ohm's law. If you if you take conductivity is equal to N E square by m tau. So here we see a very simple picture of electrical conduction reproduces Ohm's law. Isn't it? Yes. Now let us see one simple example. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1 into 10 raised to minus 7 meters square, carrying a current of 1.5 amps. Assume that each copper atom contributes roughly one conduction electron. The density of copper is given by 9 into 10 raised to 3 kg per meter cube and its atomic mass is 63.5 mu. Compare the drift speed obtained above with thermal speeds of copper atoms at ordinary temperatures, speed of propagation of electric field along the conductor which causes the drift motion. So now let us see the solution for the first part. See, the direction of drift velocity of conduction electrons is opposite to the electric field direction, isn't it? Which means electrons drift in the direction of increasing potential. So, the drift velocity Vd is given by I by NEA. So, we know E will be equal to 1.6 into 10 raised to minus 19 coulomb and A is equal to 1 into 10 raised to minus 7 meter square. I is equal to 1.5 amps. So, the density of conduction electrons N is equal to the number of atoms per cubic meter. So, a cubic meter of copper has a mass of 9 into 10 raised to 3 kg. Since 6 into 10 raised to 23 copper atoms have a mass of 63.5 kg. Okay. So, the number of atoms per cubic meter is given by 8.5 into 10 raised to 28 m raised to minus 3. Okay. So now we got the value of N, we know EA. So we can calculate the drift velocity Vd. I is 1.5. 8.5 into 10 raised to 28. 1.6 into 10 raised to minus 19. 1 into 10 raised to minus 7. So if you simplify this, we get 1.1 into 10 raised to minus 3 meter per second, which gives 1.1 millimeter per second. So this is the solution for the first part of the question. Now moving to the second part in that first one. See, at a temperature T, the thermal speed of copper atom of mass m is obtained by 1 by 2 mv square is equal to 3 by 2 kBT. Okay. And it is typically of the order of square root of kb into T by m. So where kb is Boltzmann constant, for copper at 300 K, this will be around 2 into 10 raised to 2 meter per second. So this figure, it indicates the random vibrational speeds of copper atoms in a conductor. So drift speed of electrons is much smaller, which means it is about 10 raised to minus 5 times the typical thermal speed at ordinary temperatures. Okay. Say an electric field traveling along the conductor has a speed of an electromagnetic field wave. Obviously, that is equal to 3 into 10 raised to 8 meter per second. The drift speed is in comparison extremely small. How much small means? It is small by a factor of 10 raised to minus 11. Okay. Now let us see one more simple example. That is example 2. The electron drift speed is estimated to be only a few millimeter per second for currents in the range of few amps. How then is current established almost the instant a circuit is closed? Second question. The electron drift arises due to the force experienced by electrons in the electric field inside the conductor, but force should cause acceleration. Why then do electrons acquire a steady average drift speed? Third question. If the electron drift speed is so small and the electron's charge is small, how can we still obtain large amounts of current in a conductor? When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? Are the paths of electrons straight lines between successive collisions with the positive ions of the metal in the absence of electric field, in the presence of electric field? So these are some of the, or we can say, questions which are related to electric field. So now for the first question, the electron drift speed is only few mm. So how come the circuit is closed when current is established instantly? See, electric field is established throughout the circuit almost instantly with the speed of light, causing at every point a local electron drift. So, establishment of a current does not have to wait from one end of the conductor traveling to the other end. However, it does take a little while for the current to reach its steady value. Okay. For the second question, the electron drift arises due to the force experienced by electrons in the electric field inside the conductor. That force should cause acceleration, but the electrons acquire a steady average drift speed. Why is so? See, each free electron does accelerate, increasing its drift speed until it collides with a positive ion of the metal. It loses its drift speed after collision but starts to accelerate and increases its drift speed again, only to suffer a collision again, and so on. So on the average, electrons acquire only a drift speed. Okay. If the electron drift speed is so small and the electron charge is small, how can we still obtain large amount of current? Because electron number density is enormous. It is 10 raised to 29 meter cube, electron density. Because of that, we obtain a large amount of current. Okay. Next. When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? By no means. The drift velocity is superposed over the large random velocities of electrons. Okay. Now, are the paths of electrons straight lines between the successive collisions? In the absence and in presence of electric field. See, in the absence of electric field, the paths are straight lines. But in presence of electric field, the paths in generally, they are not straight lines, they are curved lines. Okay.